Hi, I'm Jahnavi Balaji, and I'll be presenting about Ideonella, the plastic eating robot. Approximately 500 metric tons of plastic are dumped into water bodies per year. That's more plastic than the weight of 40,000 blue whales. Just for some reference, there are 26,000 blue whales alive today. Plastic takes 500 to 1,000 years to degrade, and even then, it doesn't degrade completely. It just turns into microplastics that are ingested by fish and eventually us. The degraded microplastics are carcinogenic and will eventually contaminate all of our water supply. At this rate, by 2050, there will be more plastic than fish in the sea. Ideally, we would solve this problem by preventing plastic from even entering these water bodies. However, due to the large number of water bodies and the numerous ways plastic can enter, this isn't entirely plausible. Just in Washington state alone, there are greater than 60 water bodies with close proximity to humans covering 6% of the state's total area. My research instead describes a way to solve the problem of removing floating pieces of plastic from water surfaces using unmanned surface vehicles or USV swarms without endangering marine life. My goal is to perform a literature survey of already existing robots and to propose a design for Ideonella. I would build the image detection part of the garbage collection module using a machine learning model such as Google TensorFlow. I studied and compared commercial underwater robots, such as whale shark, plankton, and jellyfish bots. I took these USVs and used and evaluated them along several parameters, such as marine life detection, plastic detection, collection of the roots of coastal trees and rock formations, and the ability to function as a robot swarm to maximize trash collection and efficiency. Next is a comparison between whale shark, plankton, and jellyfish bot. I compared them on drive, battery, range, collection volume, sensors, and costs. Plankton's drive consists of 4 electric thrusters for maximum movability, while whale sharks consist of 2 electric thrusters for eco-friendliness. The jellyfish bot consists of 3 multi-directional thrusters, while Plankton's battery consists of solar panels and electric batteries to make sure no carbon emissions occur. Whale sharks and jellyfish bot's batteries are both unknown, but the range of Plankton is unknown. Whale shark's range is 3 miles, while jellyfish range is 10,764 square feet. The collection volume of plankton is unknown, while whale shark's collection volume is 1,100 pounds. Jellyfish bot can collect up to 80 liters of oil. Its plastic unknown and can vary. Plankton sensors include anemometer, camera, sonar, and sound emitter. Whale sharks includes LiDAR, temperature, water quality, and depth. LiDAR is used to avoid any obstacles, and the rest are used to check for storms. Jellyfish bot consists of surface obstacle sensors in order to avoid any obstacles, and HD surface cameras to identify plastic. The cost of plankton jellyfish bot is unknown, but whale sharks cost is $24,600 US. Next is a proposal for the design of Ideonella. The drivetrain requirements is that it must be able to float with 1,100 pounds of garbage. It should have greater than 3-kilometer operating range and should be dual powered, both electric and solar, to avoid any carbon emissions. It should be able to operate for up to 3 hours on a single charge. Next is our sensors. Our sensors include battery level, battery temperature, propeller RPM, speed, motor temperature, sonar, LiDAR, wind speed, currents, garbage detection camera, and weight sensors. These are separated into 6 groups. The first group, battery level and battery temperature, tells us what the battery level and temperature is, what you can do to cool it down, and what the problem is because of. Propeller RPM, speed, and motor temperature tells us what speed is going at, what the rotations per minute of the propeller are, and if the motor temperature is too high. Sonar and LiDAR, our third group, tells us if there's an obstacle, how far away that obstacle is, and whether LiDAR and sonar are giving different outputs. If that's the case, it will move to a minimum of both outputs. Wind speed and currents tell us if there's a storm and how the strong currents. It tells us how strong the storm and the currents are and whether or not the USB should come back. While the garbage detection camera has an optical recognition module to identify garbage and marine animals. The weight sensor tells us how much plastic we have collected and how much more we can collect. If the USB cannot collect any more, it will return to base location. Next is our navigation and garbage collection. First, Ideonella will track to make sure that the admin has approved the mission. Then it will load the route information with its GPS sensor. It will run the USB using a GPS navigation module to navigate the route and return to base, while sonar and LiDAR will constantly be used to avoid obstacles. PSC will also search and collect waste along the route, and the emergency module will be constantly checking battery and other sensors. It will also be checking for maximum capacity or battery life, and if either one of these are low, it will return to base. Next is the design, separated into the drivetrain, control unit, navigation module, and garbage collection module. The drivetrain consists of lightweight Tesla 2170 batteries and T200 thrusters, also for its lightweightness. Solar panels also act as a backup energy source. The control unit consists of the NVIDIA Isaac kit paired with the Isaac Jetson, which has the GPU great for animal detection and avoidance. The navigation module consists of GPS, sonar, and LiDAR. GPS is used to create a route, and sonar and LiDAR avoid any obstacles on that route. The garbage collection module consists of an Intel RealSense depth camera D456 with YOLO V3 image recognition to avoid any animals and collect plastic. There is also a telescoping cylindrical suction attachment to collect plastic and waste from places that are hard to reach. For example, in banyans. Then is a garbage capture in the aluminum hull and a trap with net to prevent the plastic from escaping. Next is the design of Ideonella in more detail. As you can see, the T200 thrusters are in the back, while there's a hatch with solar panels in front that can be opened to collect plastic from inside. LiDAR, sonar, an animator, and a camera make up the front, while there's also a garbage collection module underneath it to collect all the plastic. The suction pipe is underneath all of this and collects plastic from hard-to-reach areas. Next is the code design for navigation and garbage collection. First, if the user approves start, first the GPS sensor will load the route information. It will avoid any obstacles along the way, and after route completion, it will go to docking and sorting. At the same time, the user will detect and collect any waste along the way. It will also check for how much waste capacity is left. If it's full, it will go to docking and sorting. While all this running in tandem, there is also the emergency module. If the user is in danger, it will go into boat recovery mode and communicate with the user using a cloud app. Next is the image recognition module. It's an Android app designed to simulate the garbage collection module. The phone camera represents the Intel RealSense depth camera, and the Android uses a Google TensorFlow algorithm. The app uses a phone's camera to capture and classify still images. But real-world scenarios will require a live streaming feed. As you can see, it takes a picture of marine life or plastic and labels them as either 0 marine waste or 1 marine animals. Next is what I plan to do in the future. I plan to include a more advanced ML optical recognition model for garbage collection and avoidance like YOLO V3. I will prototype the robot, including fabricating it with the hull, integrating it with the drivetrain, and control system garbage collection hardware. I would integrate the garbage detection machine learning model with a working prototype of the robot, create an end-to-end working model. I would test this model in a real-world scenario, designing and setting up docking stations for the swarms and test with multiple USVs in tandem. I would identify a safe way to dispose of plastic collected by the swarm using bacteria such as Ideonella or a variant of E. coli. The usage of GPS restricts areas of usage of robots. I plan to explore opportunities to widen the geographical scope of the robot. I also plan to include underwater trash collection of coastal areas, low depth, and not just confined to water surfaces as it is right now. If there are any questions, I will take them now.
Thank you very much, Jahnavi. So a couple questions did come in. I think you might have answered this, but I'll give you a chance to answer these questions just to clarify. First question is, are the robots digesting the plastic or just gathering it with the need to still dispose of it? I think you said just gathering at this point. Is that correct?
Yeah, it's right. Currently, the robot is still gathering it, and it would return to a docking station where bacteria such as Ideonella, which the robot is named after, or a variant of E. coli, which can digest plastic, would digest it.
Very cool. Second question that came in, how did you determine the requirements for Ideonella? So I think initially you said like 3 hours of battery life and various speeds. What were the inputs to determine those requirements?
So first, I figured out how much it would need to weigh in order to still float on the surface and still be able to collect plastic. I also compared it with other USVs that already exist, like Wayshark and Plactor. And I checked with them, and I checked what could it do, like how much battery life could it take, how much plastic could it collect, to set like a minimum standard and see how they did it and improve on that.
Great. And then last question before we move on. Again, I think you already addressed this, but I'll give you a chance to dive in a little bit more. Will this design be more appropriate for deep open water or near-shore applications, the initial design?
Currently, the initial design will be used more for water surfaces and rivers generally. It's designed for rivers where banyan roots and a lot of like rock formations are there. So it can collect plastic from these areas that would be really hard to reach otherwise.
Very cool. Love that. Those are all the questions. Thank you very much for your presentation.
Thank you.